it's kind of funny that I know exactly how many clicks. See how whoop. See how the piece of paper fits exactly between the image of me and the edge of the right edge of the camera. So I know exactly how many zoom in clicks to make it fit perfectly, and the answer is 6. Let me focus this. Let's see how many viewers we have. I'll get started in just a moment. Go over there, Bug. Go on. All right, we've reached 20. Bug, what did I tell you? Go over there. Go. Go, Bugger. Go, Bugger. Good boy. I have bags under my eyes today, for whatever reason. Need to splash my face with cold water or something. Okay. So today's lesson is on, first of all, hello, I hope you're all doing well. Today's lesson is on something called rotational inertia. So that's what I tend to call it. It's known by a couple of different names, though, so let me just give you some of the other names. Sometimes it's called moment of inertia. And sometimes it's just called inertia. So this is the one that I think IB uses and the one that I use most of the time. Okay, and it is a measure of how difficult it is to start or stop the rotation of an object. And this is in the absence of friction. Okay, so we're not referring to friction making it more difficult to start or stop. We're referring to the properties of the object itself, because friction generally has to do with the interaction between the object and its pivot point. You know, if you don't have lubrication on the axle of rotation, then that can cause a lot of friction. This is not referring to that. It's referring to the intrinsic difficulty due to the object itself. Okay, and it depends on a couple things. It depends on the amount of mass, which makes sense. Depends on the amount of mass. And it also depends on the distribution of the mass about the axis of rotation. Okay. So let me show you what that looks like. So I have a baseball bat here. Okay. And so if I'm rotating the baseball bat, then the axis of rotation is my hands, right? So this is actually a really difficult way to rotate the baseball bat, okay? Why is that? Because the mass of the baseball bat, the baseball bat is not a uniform thickness, okay? It's thicker at the end than it is at the part you hold on to. So that means that if I'm holding the baseball bat like this, most of the mass is far away from my hands. It's far away from the axis of rotation. And that makes it really difficult to swing the baseball bat. It makes it good. This is how you actually hold the baseball bat, but it makes it pretty difficult to swing. If I were to hold the baseball bat from the other end, okay, so now I'm holding it from the spot where most of the mass is close to my hands, it is much easier to swing the baseball bat around, to start and stop its rotation, okay? And the reason is that when I hold it this way, the mass is close to my hand, so it's close to the axis of rotation, okay? That makes it a lot easier. Going back to holding the baseball bat the normal way, if you've ever played baseball and you are the pitcher throws the ball, and if you're swinging and you're too slow, so you're not able to react to the baseball coming in, what the coach is going to yell at you, most likely, is to choke up. And to choke up means you don't hold the baseball bat like this, you hold it like this, okay? And so what that does is notice how it made the end of the bat move closer to my hands. So now the weight of the bat is closer to my hands, so that makes it easier to swing. It reduces the rotational inertia of the bat, so you can swing faster and hopefully react quick enough to hit the ball, okay? All right. So anyways, it depends on how the mass is distributed about the axis of rotation. That changes the rotational inertia. So let's suppose we have, I'll give you a mathematical equation for rotational inertia. Okay, so let's suppose that here's the axis of rotation, and we have a mass, which is of size m, and it's rotating about the axis of rotation, so it's going in a circle. Okay, and the size of that circle has a radius r. Okay, then the rotational inertia, which is denoted by I, of this mass is the size of the mass times the distance squared. Okay, so this is the rotational inertia of a single mass. Okay, it's the inertia of a single mass. So you can see that the farther the mass is from the axis of rotation, so if we move it farther away from the axis of rotation, then that increases the radius of the circle. So we can see that as r increases, the inertia increases substantially. So that's why choking up on a bat reduces its inertia, because you're taking that mass and you're making it move in a smaller circle, so it's easier to start and stop that rotation. Okay, so if you have more than one mass, so for example, what if you had something like a dumbbell, a dumbbell has a mass on one side, it has a mass on the other side, then the total inertia of the system, if you have more than one mass, is the sum of the mr squareds for each of the individual masses in the system. Okay? Sum over mr squared. So I'm using the sigma from mathematics, which means sum. Okay? Based on this equation, we can also get the units of rotational inertia. Okay. The units of rotational inertia are going to be units of mass times units of distance squared. So that's going to be kilogram meters squared. All right. Kilogram meters squared. So this is the basic idea for rotational inertia. Okay. So let's just do some examples to practice this. Okay. So let's suppose we have a system of 4 masses. Okay. The masses are in a square. Shoulder hurts today. Hang on, I got to reply to this text message. I'll tell you what I just. So, Mr. Hoyle said, "When do the ugly Christmas sweaters begin?" And I said, "I don't know. When did you work out last?" Get it? Because he sweats when he works out, and he's ugly. Okay, so I thought that was pretty funny. All right. Gotta amuse myself somehow. All right, so we have 4 masses in a square. So let me draw the square. So we have these 4 masses. And oh, you know what? One thing I forgot to say is that inertia is only defined for so-called rigid bodies. So when I say a rigid body, okay, when I say a rigid body, I mean a body that is not like made out of liquid or something. You wouldn't talk about the rotational inertia of liquid because liquid can flow, and as it's rotating about the axis, it's going to change shape, okay? Things that are solid, structurally sound, those are rigid bodies. So when I say a system of 4 masses, these 4 masses are linked up in such a way that it's rigid. So maybe there's like a frame around these so that they are rigidly connected to each other. You can't take this square and bend it, rotate it, etc. Okay, so let's suppose that the lengths of the sides of the square are 5 meters, And let's say that this square has a mass, or this, so each of these masses, I'm going to give them different values. So let's say this is a 2 kilogram mass, this is a 4 kilogram mass, this is a 3 kilogram mass, and this is a 1 kilogram mass. Okay? So now I'm going to define some different axes of rotation. Okay, because when we're calculating the rotational inertia, the axis of rotation is very important. Okay, so the first axis of rotation I define is going to be this one. So I'm going to call that axis A. So rotating it about that axis. Okay. The second axis of rotation, I'm going to call axis B, and it's rotating the square about that. So this axis of rotation is actually out of the plane. Okay. Axis of rotation C is going to be rotating it like this. Axis of rotation D is going to be rotating the square about its center. And axis of rotation E is going to be rotating the square about a diagonal. Okay, so let me using this calculator as an example, let me show you. I know this calculator isn't a square. Oh, you know what I could use would be a sticky note. Okay, my sticky note here is a square. Okay, so here's my sticky note. So rotating it about axis A goes through the center of the piece of paper like that. So it's like rotating it like so. All right, so rotating the piece of paper about that line that goes through its center. Okay. Rotating about axis B is like rotating around that corner. So that's kind of like keeping that corner fixed and rotating it like that. All right. Axis C is along the left side of the square. So it's kind of like opening a book. Like that. Axis D is rotating it about its center through an axis that is out of the plane of the paper. So that's holding it in the center and rotating it like that. And then axis E is rotating about the diagonal. So that's holding the corners and rotating it like this. Okay? So all these different axes of rotation have different rotational inertias because the mass is different distances from the axis of rotation. Okay, so let's see how it works. Let's suppose I wanted to calculate the rotational inertia about axis A. Okay, so for axis A, all right, I can see that this 2 kilogram mass, for example, how far is it from the axis of rotation? Well, the entire side length of the square is 5 meters. So halfway from the center to the side is going to be 2.5 meters. All right. So this 2 kilogram mass is 2.5 meters from the axis of rotation. So its inertia is going to be 2 times 2.5 squared. mr squared. Now I have to do this 3 kilogram mass. It is also 2.5 meters from the axis of rotation. So I have plus 3 times 2.5 squared. Then I have this 4 kilogram mass. It is also 2.5 meters from the axis of rotation. See, here's the axis of rotation, okay? And this point is 2.5 meters from it. So I have plus 4 times 2.5 squared. And then lastly, I have the 1 kilogram mass, which is also 2.5 meters from the axis of rotation. All right? So that gives an inertia about axis A of 62.5 kilogram meters squared. So that's for axis A. Now let's think about axis B. Axis B is rotating it about, remember, that was the one that was like this. Okay. So if I look at the 2 kilogram mass, see how the 2 kilogram mass is on the opposite corner of the square. All right. So if you have a square and the side length is 5, to go all the way across the diagonal is going to be 5 times the square root of 2. All right. And so that comes from the Pythagorean theorem, right? Because this distance is going to be square root of 5 squared plus 5 squared, which ends up being 5 times square root of 2. Okay. So when I look at this 2 kilogram mass, it's 5 square root of 2 away from the axis of rotation. So my R value is 5 root 2. If I look at the 3 kilogram mass, it's just one length of the square, one side length of the square away. So it's going to be plus 3 times 5 squared. And then the 4 kilogram mass is also just a side length away from the axis of rotation. So I have plus 4 times 5 squared. And then lastly, I have the 1 kilogram mass. Now the 1 kilogram mass is on the axis of rotation. It's on the axis of rotation. So its distance from the axis of rotation is 0. So its R value is 0. So it has no inertia. The 1 kilogram mass has no inertia. So this is an important point. If a mass is on the axis of rotation, it does not contribute to the rotational inertia of the system. Okay? So adding these up, we get 275 kilogram meters squared. So what that means is that because the rotational inertia about axis B is greater than the inertia about axis A, that means it's going to be a lot more difficult it's going to be a lot more difficult to rotate about axis B than it is to rotate about axis A. All right, let's take a look at axis C. For axis C, we can see that the axis passes through 2 of the masses. So these 2 will not contribute to the inertia rotating about axis C. All right. So only the 2 kilogram and the 4 kilogram are going to matter. So I have the 2 kilogram mass. How far is it from this axis of rotation? Type it into the chat if you know how far the 2 kilogram mass is away from this axis of rotation. I'll wait for a response. The question is, how far is the 2 kilogram mass away from axis of rotation C? Five, excellent. Thank you. So because this 2 kilogram mass is an entire side length away from the axis of rotation, so that would be 5. All right, and then similarly for the 4 kilogram mass, it is also 5 away. So again, we don't have terms for the 3 kilogram mass and the 1 kilogram mass because they are on the axis of rotation, so they have r equals 0. So working that out, we get this is an inertia of 150 kilogram meters squared. All right. Looking at axis D. Axis D was rotating the square like this, and we can see that if I'm rotating it about its center, all 4 corners are the same distance away. So all of them are going to have the same distance from the center of the square. And if this is the center, okay, we said that the entire diagonal is 5 square root of 2. So that means that half a diagonal is going to be 5 square root of 2 over 2, which is also known as 5 over root 2. Okay? So the distance from the center of the square to a corner is 5 over root 2. Okay? And all 4 masses are the same distance away from the center because it's a square. So the rotational inertia about axis D is going to be 3 times 5 over root 2 squared plus 4 times 5 over root 2 squared plus 1 times 5 over root 2 squared plus, what's the one I missed? 2 times 5 over root 2 squared. So that gives an inertia of 125 kilogram meters squared. All right, so we have one more axis to consider, which is axis E. So if I'm rotating about axis E, I can see that the bottom right corner, the bottom left and the top right corner of the square are on the axis of rotation. So it's only these 2 corners that are going to contribute to the rotational inertia. Okay, so in this case, it's only the 3 kilogram and the 4 kilogram. Now, how far away are those points from the axis of rotation? Well, here's my axis of rotation. The distance of the corner from that is 5 over root 2. Okay, so I have the 3 kilogram mass, and it is 5 over root 2 from the axis of rotation. Okay, and then there's the 4 kilogram mass, which is also 5 over root 2 from the axis of rotation. So that gives an inertia of 87.5 kilogram meters squared. Okay? So let me ask you, I'll type it into the chat if you know the answer. Which axis is going to be easiest? Is it going to be easiest to rotate this square about? Which of these axes is it going to be easiest to rotate the square about? Excellent. Yeah, axis A. And the reason is that it has, out of these 5, it has the smallest rotational inertia. Okay? All right. So I'm actually almost done with my lesson here. But one thing I did want to let you know is that odd shapes have their inertia calculated. Using calculus. So, and calculus is not part of this class. Okay, calculus is not part of this class, but we will encounter some of these shapes. Okay, so I'm just going to give you the inertias. You don't have to know where they come from, but you do have to use them occasionally. So in a couple of lectures, we're going to use some of these inertias for odd shapes. So for example, what if you have a solid disk? Okay, so you have a solid disk, and so it's a solid disk, and you rotate that disk about its center, like that. Then the inertia of that solid disk is 1/2 times its mass times its radius squared. Okay. If you have a solid sphere, so a solid sphere looks like this. And you rotate it about an axis through its center. Like that. And I'll do this because it's a solid sphere. Then the rotational inertia is 2/5 mr squared. Okay. If you have a hollow sphere, so it's just a spherical shell, and you rotate it about its center, then the inertia is 2/3 mr squared. And I think those are the ones that I want you to know, or I want you to have written down for now. You can look up rotational inertia on Wikipedia, and it'll give you the inertia for tons and tons and tons of different shapes. But this is sufficient. Okay. Oh my gosh. So we're not going to use these today. In today's quiz, you're going to be doing examples such as these ones. All right, but in a few lessons, you're going to need to know the inertia for these things. So make sure you have them written down. So that's my lesson for today, and I will see you in the Zoom room.